All right, so here's where we left off. We went through and we were looking at the section 2.7 in the textbook, figuring out how to read it. Some of the things are very wordy, very mathematically precise and all that sort of stuff. Sometimes when they're doing some work in an example, they'll skip some steps, so we'd want to make sure that we understand, how they got from one to the next. It would be surprising at this point if there were any errors in the textbook, so if you don't get how they went from one line to the next line, you've got to figure out the algebra that went behind that to simplify or to factor or whatever it happened to be, okay? So what we did last time, actually, I'm hoping that you thought about this a little bit. We talked about something called the derivative, and we talked about how it can find the instantaneous rate of change for a function, or on the curve, that relates to the slope of the tangent line at a particular point. And what we did is something very similar to what we did in section 2.1. We said, well, let's just think about 2 points on this curve. So I've got an x value here and an x value here. They both correspond to y values. Let's find the slope of the secant, and then let's just slide those 2 points closer together. So as we slide those 2 points closer together, the slope of the secant should approach the slope of the tangent, okay? And then we controlled that process in a couple of different ways. The first way we learned how to do it was this way right here, where we were actually sliding that point x closer to the point of interest A. And then a more useful, generally because it's easier to use via simplification, is something like this. And this is called the limit of the difference quotient. And if you ask somebody for the definition of the derivative, that's probably the one that they would give you. Okay, you can use either one, but again, this one's much better because most of us are better at simplifying than we are at factoring and using these obscure algebraic techniques that sometimes come up when we're doing this one right here. Again, it's not that this isn't useful, not that we'll never use it. It's just that this generally is a lot easier to find. So this is the derivative at A. We call that f prime of A. And the cool part about this is if you find it in general, like we did on this problem right here, what we've done is we started off with this function right here, x squared minus 8x plus 9. And we actually found a rule, the derivative of that function. We call it f prime, and I think I also wrote this down. We could write this as f prime of x and just change the variable. I think we talked about the fact that we could call that a dummy variable. What we've done here is doing this process right here, just in those couple of lines there, we've produced a function that will tell you the instantaneous rate of change or the slope of the curve at any point you want. So if you want to know the slope at 2, plug in a 2. If you want to know the slope at 7, plug in a 7. Okay? Any questions there? That's just kind of a summary of what we talked about last time. Okay, so what I'd like to do today is I'd like to finish up talking about this. Kind of reading through this section, and then I'd like to take a look at a couple of problems from 2.7, and if you've got questions from 2.7 or any other sections, we could take them at that point, okay? So, let's see, where did we leave off? Where did we leave off reading? Who read last? Peter, did you read? You did?
I did.
Okay, Brad, did you? Okay, Brad, could you read, do you have your notes?
Yep.
Okay, could you read that paragraph right there we defined?
We define the tangent line to the curve y equals f of x at the point P of A, F, and A to be the line that passes through P and has slope m given by equation 1 or 2. Since by definition 4, this is the same as the derivative f prime of A, we can now say the following.
Okay, so again, that's tough to read. All that math, again, we talked about how you can read through that and say, I'm stumbling through this. How could I shorten this so my brain can really grasp this? Okay, so we define the tangent to the curve. Okay, do we need to know that we say y equals f of x is the curve? Not really. I mean, when we get down in the nitty gritty, we're going to need that. But we could say define the tangent to the curve at that point. We don't need to worry about that we denote the point that way. So we define the tangent to the curve at that point to be the line that passes through that point and has the slope given by equation 1 or 2. Well, let's come back up here and take a look at equation 1 or 2. Okay? That was all the way up here. Let's see, there's 2. And let's see, yeah, that was 1 right there. okay? So all it's talking about is using those formulas that we just got used to and using that definition 4, that's the derivative, that's the slope of the curve, okay? So we can say this, it says the tangent line to that curve at that point is the line that goes through that point and has a slope that's equal to the derivative at that point. That's all that means, okay? So it's got to go through that point and it's got to have the slope or the derivative equals the slope at that point, okay? And then it says, if we use the point slope form of the equation of the line, we can write the equation of the line tangent to the curve this way. And that's how we wrote those before, right? Didn't we use y minus y1 equals mx minus x1? Really, the only thing that they've replaced here is instead of using an x coordinate, they called this an a. Instead of using an y coordinate, they called this f of a. And what did they put in place of the slope? The derivative. The derivative at that point. So, what's that? It is genius. Why is this genius, Ben?
Because you can do that for just about any other. It's just like the other equation that you gave us. You can do this for any function.
Okay, you can do this for any function, and here's why I think this is genius. Notice that everything in this tangent line is defined according to where we are in the x direction. So if you tell me what the x is, so say I wanted you to find the slope at x equals 7, okay, or in this case, a equals 7, okay, plug a 7 in here, that would be f of 7, that would be the y coordinate when we plug in a 7 into the original function, okay, notice that's an f, and then this is f prime at 7, okay, so this is the function value at x equals a, and this right here is the derivative, f prime at x equals a, okay? So you tell me what the point is, you tell me what x is, and I can tell you everything else. I'm going to find the function value using the original function, and I'm going to find the slope using the derivative, okay? So think about it in those terms. You tell me what the x coordinate is, I'm going to find the y coordinate so I know what point it goes through, and I'm going to use the derivative to find the slope. If you go back and look at your notes from chapter 1, or you go back and watch that video again, okay, we said there are two things that you need to find the slope of a line. Point and a slope. Finding the point is a pre-calculus problem. Finding the slope is now a calculus problem because we're going to use what to find the slope? The derivative. It's that simple, okay? So it says find an equation of the tangent line to that function right there at this point right here. That's a. That's f of a. They've done some of the work for us. They told us what a is. They gave us f of a. The only thing we need to do is find the slope. And how are we going to find the slope? Plug it into this formula that we had up here. Okay? So that's really all they're doing at this point right here, is they're just plugging in that x value. So notice they plug in a 3. They get that the slope is -2. And notice where each one of these things comes in. They then go through and solve it, and they put it in slope-intercept form. That's kind of nice for putting it in the calculator or just relating it to what you know from pre-calculus. And this point right here is 3, -6, and there's our tangent line. And does it look like it touches that point just at that, or that curve just at that one point? Okay? Any questions? This isn't too bad, is it? Make sense? Okay. So then they start talking about rates of change, and you'll remember last week it said the reason we give this a special name is because this process of finding rates of change and finding derivatives comes up so often in science, in math, in physics, all sorts of places. That's why we want to know how to do this, okay? So here's this, and I'll go ahead and read this. It says, suppose y is a quantity that depends on another quantity x. Y is a function of x, basically. Thus, y is a function of x, and we write y equals f of x. Okay? X changes from x1 to x2, then the change in x, also called an increment, okay? This is going to come up again, but the increment for x is how much the x coordinates change, okay? So we call this delta x, okay? Delta for d, this is a capital D, capital delta, okay? That triangle is delta. It just stands for the difference in the x's. So the difference would just be, we literally subtract the two x coordinates, okay? The corresponding change in y, again, we'll call this delta y. is going to be the difference in the two y coordinates. So f of x2 minus f of x1. So delta y over delta x, or change in y over change in x, difference in y over difference in x, is going to be the difference in the y coordinates over the difference in the x coordinates. Okay? Should look really familiar. All that is slope formula. Okay? And then it talks about that being the average rate of change. Okay, so I've got my x and x coordinates right here. Again, we're finding the slope between those 2 points right there. That would be the average rate of change. And what we want to do here is we want to move those 2 points closer and closer together. So if the denominator is delta x, and that would control how close these 2 points are together, we want to make that smaller and smaller and smaller. That's why we have delta x go to 0. Okay? So this would be, I mean, if you wanted to think of it, this is kind of like another definition for the derivative. Okay? It's called the instantaneous rate of change. But if you let the difference between the two x coordinates go to 0, that's going to be the slope of the tangent line, or that's going to be the instantaneous rate of change. Okay, that's going to be the derivative. Okay, we're just looking at this in just a slightly different setting. Okay, and then down here, I'm going to skip this paragraph there. It says the derivative f prime of a is the instantaneous rate of change of f of x with respect to x when x equals a. Okay, now, does this sound a lot different than what we've been talking about, or just a little bit different than what we've been talking about? No response. That's
delta
fabulous. What's that?
The weird delta y,
Well,
delta x.
Yeah, this stuff right here. I mean, just take what we've been talking about for the last 2 minutes altogether. Does it sound a lot different than what we've been talking about, or just a little bit?
A little bit.
Just a little bit, okay? All they're emphasizing here is that you can use the derivative to represent the instantaneous rate of change. That's it, okay? Which we kind of already brushed on before. So the derivative is the instantaneous rate of change. And then it says in connection with the first interpretation, if you graphed that function, whatever it was, then the derivative would represent the slope of the tangent, okay? So here's a particular example, okay? Let's see, Jen, would you read that one where it says in particular?
In particular, if s equals f of t is the position function of the particle that moves along the straight line, then f prime of a is the rate of change of the displacement s with respect to the time t. In other words, f prime of a is the velocity of the particle at time t equals a. The speed of the particle is the absolute value of the velocity, that is f prime of a.
An absolute value, right? Okay, all right. So again, very wordy here. This is what we're after. Okay, if you start with a position function and then you find the derivative, what is the derivative of a position function? What does it give you? It gives you the slope. We could talk about it in terms of slope if we were to graph it. It's right in the paragraph. So,
The velocity.
okay, it gives you the velocity. Okay? So if you have a position function that's given as a function of t, so like s of t or f of t, whatever it happens to be, again, we normally use s. If you find the derivative of position, it will give you the velocity. Okay, now Juan, what's velocity?
Speed and direction.
Speed and direction. How fast you're going and in which direction you're headed. Okay, normally we do things in a line, so we're either headed in the positive direction or the negative direction, whatever that coordinate system happens to be, or we're going up or we're going down. Okay, so velocity has two components. Okay, the first part is the magnitude, how fast you're going. Okay, and then the sign will tell you which direction. Okay, most of the time we think of up as positive and down as negative, right as positive, left as negative. Okay. If we take the absolute value of that, then that will tell us just how fast, or we refer to that as the speed. And that's why this is an absolute value. Okay? So the next example is kind of a basic example. It's a manufacturing problem, and here's what we've got. Okay? Now think about the quantities that are being measured here. Okay? And think about how one variable is a function of another variable. It says a manufacturer produces bolts of fabric with a fixed width. Okay, so Fabric is just coming off the machines, you know, and it's always 3 feet wide or 10 feet wide or whatever it happens to be. Okay, the cost of producing X yards of this fabric. So as 1 yard rolls off, okay, there's 1 yard, then 2 yards, and so forth. Okay, the cost for producing that just continues to add up. Okay, so cost is a function of X. Okay, it says what is the meaning of the derivative f prime of X. Okay, now let's go ahead and do it in their vocabulary. Okay, okay, this is cost as a function of X. And X is in yards. So you tell me how many yards have rolled off here, and I can tell you how much it's going to cost. Okay, it says, what is the meaning of the derivative f prime of X? So if this is cost, what if we find f prime of X? What if we find the derivative? The derivative is a slope. It's a rate. So if somebody says rate, you're going to think slope. If somebody says derivative, think slope, think rate. Okay, think all those things are interchangeable. Okay, so if we found the derivative of the cost, okay, are derivatives average rates or are they instantaneous rates? Instantaneous. So it's going to be the instantaneous. Okay, and I'm going to say this, ROC, rate of change. Instantaneous rate of change for the cost. And then it says, what are the units? Okay, and it has, I mean, the answer is right down below, right? Okay, so we could just read through this, but it would be great if we thought about it before we look down below. Okay, think about how we'd find the derivative. It's literally the difference in the cost, which is represented in dollars, over the difference in X represents yards. So it's going to be the rate of change in dollars per yard. Okay. So usually what would happen in a manufacturing process is that rate of change, okay, how much the price is going up or down, the more you make, usually what happens to the cost per yard, per unit. Yeah.
What does this bottom say?
Sorry. This is dollars per yard. Okay. So dollars on the top, that would be the rate of change of cost, and on the bottom, it's a difference in the yards. Okay, so normally it gets cheaper per yard. Okay, the unit cost goes down. All right. It says in practical terms, what does it mean to say that f prime of 1,000 equals 9? So that's on the next page. Let's not flip there till we think about this for just a second. F prime of 1,000. Okay, these are X values that we're plugging in. So what does the 1,000 mean in the context of this problem? Okay, so we've produced 1,000 yards. Okay, and are we talking about the original function that tells you what the cost of producing 1,000 yards is, or are we talking about the derivative, the rate of change of cost? Talking about the derivative. Okay, so when we produce 1,000 yards, this is a rate of change is 9. Rate of change is 9. 9 what? Okay, $9 per yard. So the instantaneous rate of change when we've produced 1,000 yards of material is $9 per yard. Okay? And it says, which do you think is greater? Okay, and again, keeping in mind what's going on here. F prime of 50, the instantaneous rate of change, the cost per yard at 50, 500, or 5,000? Which one is greater? Cost per yard at 50 yards, cost per yard 500 yards or cost per yard at 5,000? Juan, what do you think? Why do you think 50?
Because it costs more to produce less yards.
Okay, costs more to produce less. Okay, in order to get in business, you've got to have the equipment and manufacturing space and stuff like that. So even if you didn't produce anything and just said, hey, I'm going to put a fabric company together, but we're not going to do anything, it's still going to cost you a lot. Okay, that first yard costs a ton because it has to pay for everything in the building, the material and everything, okay, and you only made 1 yard. Okay, the more you make, the more you can spread out all that overhead cost over more yards of material that you've made. Okay, so that to some extent, and we'll come back to this later on, to some extent explains the economies of scale. So it says at 50 yards, yep, that would be greater than 500, and kind of goes through that explanation there. Okay, and greater than 5,000 as well. Okay. All right, let's see. Okay, so this one is about the national debt, and it says D of T. And the thing I like about this one here is, why did they choose D? Why not F? Debt. Okay, it's really nice when we name a function something that represents what we're after. So we've got D of T. So this means the debt is a function of time. You tell me what the time period is or where I am in time, and I'll tell you what the debt is. Okay? So let's see, it says D of T, that's the U.S. national debt at time T. The table in the margin gives approximate values for this function by providing end-of-year estimates in billions of dollars, okay, from 1980 to 2005. Interpret and estimate the value of D prime of 1990. Okay? Now, this is a really good example because in order to get this, you've got to understand rates of change, and you've got to understand how we're taking those rates of change and looking at them in different respects. Okay? We're looking at it as a rate of change, which we could think of graphically as the slope, and the notation that they used here was the notation for the derivative. So what they're saying is find the derivative of that debt function in 1990. But in order to do that, you're going to have to think about how does this data relate to the derivative? Well, if we were to graph this, what would we be trying to find at 1990 on the graph? The rate, or what's another word for rate? The slope, okay? So let's do this. If 1990 is right here, should we do 1990, and that's 3233.33, and then in 1995, it's, I'm going to write it right here, 4974.0. Should I take the two of those, find the slope between the two of those? Because that's a very simple process to do. Not nice numbers, but a very simple process. Should I do that and call it quits? Probably not. Because that's information about 1990 and 1995, but does it contain any information about what happened, what the rates were, or what the slope was on this graph before 1990? Nope. Okay, so maybe consider 1985. We could put this point on here, and that one is 1945.9. And I'm going to move it up here just for the heck of it. Okay, I could find that slope. So I'll call this D prime 1, and I'll call this D prime 2. So I can find two different slopes there. Are both of those good estimates? Which one do you want to use? Or do you want to do something else? Probably ought to do something else. What else could we do? What's that? Sure, you could do another one. Okay. What's the problem with including another point like at the year 2000 if we're interested in 1990? 1990 and 2000, they're pretty far away. Okay. You're definitely going to use this information right here, but what else could we do with this information that probably would be more accurate than just finding that slope and that slope there, and then figuring out which one we want to use? Are these the only secant lines you could find the slopes of on this graph? Couldn't we do this? Couldn't we split the difference? What if we went from 85 to 95? Wouldn't that contain information about what happened before 1990 and information about after? You could do that. Or you could find the two of those separately and then do what with it? Average the two of them. Okay? You might want to think about whether or not we'd get the same answer as just going from 1985 to 1990. Okay? So here's what they did. Let's see, it lies somewhere between that many. Okay. So they did the difference between, notice they've got 1990 in every one of these calculations. They did back 10 years, back 5 years, forward 5 years, forward 10 years, and then forward 15 years. Okay? I think this probably is the most reasonable thing to do, to go 5 years forward and 5 years back. But can you see what they did there? Okay. What are the units in that? Yeah, since this is the debt in dollars and this is in years, it's going to be dollars per year. Okay? It's going to be an estimate for how much the debt was increasing per year right around 1990. Okay. Any questions? Okay, so if we do something like this, and we told you what D and T are, again, symbolically it might look weird, but all this means is, in this case, difference in the debts over the difference in the times. It's a very short way to write a slope calculation. y2 minus y1 over x2 minus x1. Okay. All right. And then it says, let's see right here. Braden, will you read that? That's a long one. Will you read that paragraph right there?
Examples 3, 6, and 7, we saw 3 specific examples of rates of change. Velocity of an object is the rate of change of displacement with respect to time. Marginal cost is the rate of change of production cost with respect to the number of items produced. The rate of change of the debt with respect to time is of interest in economics. Here's a small sample of other rates of change.
Okay, so stop right there for just a second, and then I'll have you read that again, or continue reading that. So the rate of change of displacement with respect to time, if you have a position function and you find the instantaneous rate of change, you find the derivative, that's going to give you the velocity. Okay, or at the very least the speed. Okay, we're going to use position and velocity quite a bit, so please don't forget that. Okay, it also talks about marginal cost. If you have a cost function and you find the derivative, marginal cost is something that's used all the time in economics and in business. Okay, how are the costs changing? Okay, because if our cost is here, but the marginal cost is like this, as a business person, you don't want that. You want your costs going down. Okay, and then it says the one with debt. Okay, and knowing how to figure out and calculate. Okay, what are the units on the top and what are the units on the bottom? Okay, that's key to figuring out how a lot of these problems, especially the story problems, work. If you can kind of attach, okay, I know what the numerator is, I know what the denominator, here are the units that I'm looking for, that can tend to make a little bit more sense. So some other examples there in physics, what does it say? So it says the rate of change with work, right there, right where you left off. Yeah, if you would.
In physics, the rate of change of work with respect to time is called power. Chemists who study chemical reaction are interested in the rate of change of the concentration of a reactant with respect to time, called the rate of reaction. A biologist is interested in the rate of change of the population of a colony of bacteria with respect to time. In fact, the computation of rates of change is important in all of the natural sciences, the engineering, and even the social sciences. Further examples will be given in section 3.7.
Okay, so what's going to happen between now and 3.7 is we're going to learn a bunch of rules to find derivatives for different types of functions. And they're not as simple as some of the ones that we've gone over so far, but their applications are huge. You can use them in physics, you can use them in biology, you can use them in economics. So we'll see some story problems crop back up, probably using similar examples like speed, velocity, position. okay, like cost and marginal cost, different things like that, and that will come up again in 3.7, okay? And then Alan, can you read that last paragraph right there?
All these rates of change are derivatives and can therefore be interpreted as slope of tangents. This given added significance in the solution of the tangent problem. Whenever we solve a problem involving tangent lines, we are not just solving a problem in geometry, we are also implicating solving a great variety of problems involving rates of change in science and engineering.
Okay, so all of those rates of change, you can interpret those as derivatives. So we want to be comfortable finding the derivative algebraically, using calculus and limits and all that sort of stuff, and then understanding what that means on the graph. Because really, every time you do that, this little process right here that we looked at the very beginning, that process right there, it's a whole bunch of algebra. We weren't really thinking of in terms of geometry, but that's really what's going on. Think about where we developed this. We were looking at a curve. We had 2 points. We computed the slope of the secant, and then we slid those 2 points closer and closer together, and we want to find what happens there. Okay, so when we're talking about the derivative, it's going to have a geometric interpretation, okay, and also an interpretation in the context of the problem, like an instantaneous rate of change, dollars per year, cost per yard, all that sort of stuff. Okay. So did anybody try the homework? Are there any questions or anything? Or do you just want me to pick a couple? Okay, is number 3 on your assignment? Okay, let's take a look at problem number 3. Let's read it first of all, and then notice that it says using definition 1 and using equation number 2. It says find the equation of the tangent line in part A and then graph the parabola. So we did something like this the other day. So here's what we've got. We've got this function right here, and we've got that point right there. So you'll notice that they gave us a and f of a. They gave us the x and the y coordinate, if you want to think of it that way. And then we need to find the slope. So if we're going to find the slope, what do we need to do to that equation right there? To that function? We need to find the derivative, okay? We need to find the derivative. So let's go ahead and do that. And then if you'd flip back, we need to have, it said we want to find it using definition 1 and equation 2. So definition number 1, and let's find equation 2. So would you look back and find those while I write this down? Okay, who's got definition 1? Yeah, Alan.
X minus f of a over x minus a.
Okay, it's that one right there. And we want to find the slope there, so we want to find the limit as what goes to what? As x approaches a. Okay? And that's going to be the derivative at a, right? Okay, now, on this problem, what is a? A is 1. Okay? So a equals 1, f of a equals 3. So we've got these two pieces right here. Now, in my opinion, okay, this is how they would like you to set this up. I don't mind if you do this on some of them. So you can set it up this way. If you want to know what f prime at a is, or f prime at 1, what the slope of the curve is at 1, at x equals 1, then you do this. You do f of x, which is 4 minus x squared, minus what is f of 1? Oh, it's 4x, sorry. Missed the x there. Good there. And what is f of 1? 3. And what goes on the bottom? X minus, what's a in this case? 1. Okay? So, okay, that's how they'd like you to set this up. This is a nice problem. Okay, it's got numbers in it and everything. What would be really nice is if you could do it this way also. This would be 4x minus x squared minus, what would f of a be? Not this a, any a. It would just be what we get when we plug an a in here, right? So it would just be 4a minus a squared, correct? And the bottom would be x minus a. Whoops, I want to put a, forgot something here. Limit as x goes to 1, right? And on this one, it would be limit as x goes to a. So the end result of this one is going to be a number. A number is just going to drop right out. The end result of this one is going to be a formula, another function, okay? Both of those would be really good things to be able to do, but let's take a look at this one up here. So here's what I get. I get 4 minus x squared minus 3 over x minus 1, and I want to find the limit as x approaches 1. So this is going to be 1 minus, oops, let me just save room for that limit in there. What's that?
You forgot the x again.
Oh, I did, didn't I? Thanks. Okay, so this is going to be the limit as x approaches 1. I'm going to write this as negative x squared plus 4x minus 3 over x minus 1. Can I evaluate that by substitution? Nope. Okay, and when you're doing these difference quotients, you're never going to be able to evaluate it by substitution. So let's do a little bit of work here. The first thing you'd probably want to do is you'd probably be better off factoring this out. If you don't need to factor it out, that's totally fine. So that's going to be a minus 4x and a plus 3. We'll then factor that right there. So this is going to be the limit as x approaches 1, negative, and then I need two numbers that multiply to be positive 3 that combine to be negative 4. So that's going to be a minus 1 and a minus 3. Whoops. Getting ahead of myself. And then this will happen every single time. The algebra is going to work like this, especially on a polynomial here. So we end up with negative x plus 3. And then we take the limit as x approaches 1. So this is going to approach negative 1. This is going to approach positive 3. So our answer is 2. Okay, they wanted the equation of the tangent line, right? What two things do you need to write the equation of the tangent line? Slope and a point. Okay, there's the point. There's the slope that you're going to use. Okay, so you're all set to go there. I'm going to change colors here. What was equation number 2?
Limit as h approaches 0 of f of a plus h minus f of a over h.
So they want us to find the derivative that way, okay, using the other difference quotient. Okay, so I'm going to set it up this way. So let's do it for that a right there for 1. So f prime at 1 is going to be the limit as h approaches 0. And let's see, it's got to be 1 plus h. That means whatever this is, I'm going to plug in a 1 plus h wherever there's an x, right? So this is a 4, 1 plus h, minus 1 plus h quantity squared, and then minus f of a. Well, I'm plugging in a 1 for a into the original function. Get 3, right? All over h. So this is going to be 4 plus 4h. Careful here. What do we get when we square this out?
1 squared plus 2h.
They were all positive. Put a negative in front of every one of them. Is that all right? Skipping too much work there? Are we okay? All over h. Again, you couldn't evaluate this by substitution here. You still can't evaluate it by substitution, but let's start crossing some things off. There's a minus 1, a minus 3, and a positive 4. Those all cancel each other out. Okay, I'm left with 4h minus 2h, so that's going to be 2h minus h squared over h. Factor out the h and cancel it off, so I end up with this. The limit as h approaches 0 of 2 minus h. That goes to 2, that goes to 0, so our answer is 2 in either case. Okay? Okay, so that was definition 1 here. This is equation 2. Which one on this particular example looks like it's easier? Suppose it depends on your perspective, okay? This wasn't too bad. We just did a little bit of factoring. Okay, we've done limits like that quite a bit. Okay, this is a bunch of simplification. Okay, not too bad as long as you square this out, and that will come up over and over and over again, so please make sure you know how to square a binomial. Okay, if we did this, we'll end up with a formula. Or if we did this, change colors again. If I did f prime at a equals the limit as h approaches 0, okay, it's going to look something like this. It's going to be 4a plus h minus a plus h quantity squared minus f of a, so that's going to be 4a minus a squared all over h. Okay, if you do this, you're also going to end up with a formula. You're going to end up with a new function. It would be more complicated than the two that we did right here, but what would be nice about finding a formula? Plug in the number, okay? This process that we did up here and this process that we did right here will only find the derivative. It will only find the slope of the curve at 1, at a equals 1. If we did it like this, it will give us a formula with an a in it, and then we can find the slope anywhere we want. Okay? This is a good skill. This is what we're after in the long run. Okay? So I would do a couple this way, and then I'd try and do some of them doing it in general and then plugging in the point of interest after the fact. Okay, are there any questions about that? Okay, let me go ahead and do this one. Let's finish this off and see what we end up with. So this would be 4x minus x squared. This is going to be minus 4a, and this is going to be plus a squared over x minus a. Okay. Can you plug in an a for x? Nope, you get a 0 in the denominator. So we've got to simplify this somehow. Any ideas? What's that? Very good. Okay, so here's what we're going to do. I'm going to write this as negative x squared. What would be next, Peter?
Plus 4x.
Yeah, let's see. You want to do the plus 4x? Okay. Suppose you could do that. What next?
Plus a squared.
Plus a squared
Minus 4a.
minus 4a. That's all of those. And then I've got an x minus a. Now what?
Would you factor out an x for the first one?
Okay. So I'm going to factor out. Tell you what. How about we pull out a negative x? Is that okay? Take out the leading sign. So if I take out a negative x, then I'm left with an x minus a 4. Then what?
You pull out a positive a.
Pull out a positive a, and I'm left with an a minus 4. Right? Okay. Then I've got an x minus a here. So they both have, let's see, they have anything in common here? Okay. So is that the right way to group?
No.
Nope. Okay.
I put a squared minus x squared plus
There you go.
4x minus 4a.
Okay. So here's the trouble. I think most people would think that this was a little bit easier because we've done problems like that. Okay. The trouble with this, with that definition one, that first way, remember I said that wasn't the favored way. That's not the way I like to do it, because you've got to know a lot about algebra. And if you bark up the wrong tree like we did right here, you end up in a dead end. Okay, so what did you do?
I put the a squared and the negative x squared together.
Okay, so let's do negative x squared plus a squared, and then we'll write the plus 4x and the minus 4a. Good?
And then the negative x squared plus a squared, you can do that as difference of squares.
Okay, so I'm going to factor out a negative and write this as x squared minus a squared, and then out of here we're going to take out a 4 and we're left with an x minus a. And on the bottom is an x minus a. Now, why is that advantageous? Notice that those have something in common, and go ahead and finish. How do we get this to have a factor of x minus a?
So x plus a and multiplied by.
Okay, this is a difference of squares. So this is minus x minus a, x plus a, plus 4, x minus a. Good there? Okay, now I can cancel. I could factor it out, or I can cancel those all at the same time. Is that okay? And I end up with, let's see, this is going to be a minus x minus an a plus 4. So this is, and we're taking the limit as x goes to what? So that goes to negative a. That's negative a, and that's plus 4. So what's my little formula here? Negative 2a plus 4. Now, what happens if I plug in, what was the point of interest on this particular problem? Whoops. It was a 1. What happens if you plug in a 1? You get a 2. You get the same answer. Okay, now, if you tried to do this one, okay, the cool thing about this is this problem right here is going to be no more work than that one right there. It's going to work in a very, very similar fashion. It's a lot easier to do that one in general than it was to do this one right here. Okay, so do you see why I like that definition 2 a little better? Okay, you might want to try that. So tomorrow I'll just take questions from 2.7, from the review, answer any questions you've got. I would make sure that you've printed off and tried to work on that review a little bit so you know what questions you need to have answered tomorrow, and then the test is Wednesday. Okay?
So 2.7 is due on Wednesday.
2.7 is due on Wednesday also, yeah. Because we didn't really finish it until today. Okay? All right, thank you.